everyone. Welcome to part 2 of cloud security. After understanding different cloud security threats, let us move to the protection side, cloud security mechanisms. These mechanisms are the technologies and methods used to secure cloud systems and protect data from attacks. In this unit, we will discuss important security mechanisms such as encryption, hashing, digital signature, public key infrastructure, identity and access management, and single sign-on. In the next few slides, we will study each of these mechanisms in detail. Now let us discuss one of the most important security mechanisms called encryption. Encryption is the process of converting readable data called plain text into an unreadable format called ciphertext. The main purpose of encryption is to protect confidential information from unauthorized access. For example, when you enter your banking password online, the information is encrypted before transmission so that attackers cannot understand it even if they intercept the data. Encryption uses a secret value called a key to convert plain text into ciphertext. Only authorized users with the correct key can decrypt the information back to its original form. Now look at the diagram shown here. The cloud service consumer sends an encrypted message towards the cloud service. Even though a malicious service agent intercepts the message, the attacker cannot understand the contents because the data is encrypted. So encryption mainly helps maintain confidentiality in cloud computation. There are mainly two types of encryption: symmetric encryption and asymmetric encryption. First is symmetric encryption. Here, the same key is used for both encryption and decryption. Think of it like a locker where the same key is used to lock and unlock the door. Both the sender and receiver must know that shared secret. This method is faster and commonly used for protecting large amounts of data. But the challenge is securely sharing the key between the users. About the symmetric encryption, it does not provide non-repetition because both users use the same key. So later it becomes difficult to prove who actually sent the message. Next is asymmetric encryption. Here, two different keys are used, a public key and a private key. The public key is openly available while the private key is kept secret by the owner. If data is encrypted using the public key, it can only be decrypted using the corresponding private key. Similarly, if a document is encrypted using the private key, it can be verified using the public key. Since two keys are involved, asymmetric encryption provides stronger security, but it is slower compared to symmetric encryption. Let us discuss another important security mechanism called hashing. Unlike encryption, hashing is a one-way process. Once data is converted into a hash value, it cannot be reversed back to the original message. Hashing is mainly used to verify data integrity. Think of it like a fingerprint. Every person has a unique fingerprint, and even a small change creates a completely different result. Similarly, when a message is passed through a hashing algorithm, it generates a fixed length value called a message digest. If even a single character in the original message changes, the generated hash value also changes completely. Now look at the diagram shown here. A malicious service agent intercepts and modifies the message during transmission. When the firewall or receiver generates the hash again, the hash values do not match, revealing that the message was altered. So, hashing helps detect tampering and maintain data integrity. Now, coming to the digital signature, a digital signature is used to verify both authenticity and integrity of a message. It works using a combination of hashing and asymmetric encryption. Think of it like signing an important document manually. Your signature helps others confirm that the document actually came from you and was not modified later. Similarly, in digital communication, the sender creates a message digest using hashing and encrypts using a private key. This becomes digital signature attached to the message. Now look at the diagram. Cloud service consumer B sends a digitally signed message, but during transmission, trusted attacker A modifies the message. When virtual server B verifies the digital signature, the verification fails because the message contents were altered. As a result, the message is identified as invalid and rejected. Next, public key infrastructure. It is a framework used to manage public key cryptography securely in large systems. In asymmetric encryption, users have public keys and private keys. But an important question arises. How can we trust that a public key actually belongs to the correct person? PKI solves this problem. Think of it like an ID card issued by a trusted authority such as a government organization or university. When we see the official seal on the ID card, we trust the identity of the person. Similarly, PKI uses something called a digital certificate. A digital certificate contains the public key, owner identity information, and certificate validity details. These certificates are usually issued and digitally signed by a trusted organization called a certificate authority. So when users receive a digital certificate, they can verify that the public key truly belongs to the correct owner. PKI is widely used in secure websites, online banking, cloud security, and encrypted communication systems. Now let us understand the diagram showing how a digital certificate is generated in a public key infrastructure system. The process starts with the cloud consumer. The cloud consumer already has a private key and a public key. Remember, the private key is kept secret while the public key can be shared. Now, the cloud consumer sends a certificate request to the certificate authority, commonly called the CA. This request contains the cloud consumer's public key and identity related information called cloud consumer data. Next, the certificate authority verifies the information provided by the cloud consumer. After verification, the certificate authority applies a hashing mechanism to generate the hash value from the consumer data and public key. Then, the CA encrypts this hash using the CA's private key. This becomes the certificate authority digital signature. Finally, the CA creates the digital certificate by combining the cloud consumer's public key, the cloud consumer information, certificate properties such as validity period, and the CA digital signature. This completed certificate is then issued back to the cloud consumer. Now, any user receiving the certificate can verify the identity of the cloud consumer and the authenticity of the public key because the certificate is signed by the trusted certificate authority. This slide explains the importance of trust in public key infrastructure systems. Usually, digital certificates are issued by trusted certificate authorities such as VeriSign and Comodo. These organizations are trusted because they follow strict security procedures while issuing certificates. Large companies like Microsoft can also act as their own certificate authority and issue certificates to their users or clients. Even individual users can generate certificates if they have the required software tools. But simply creating a certificate is not enough. The important factor is trust. Think of it like an ID card. An ID card issued by a well-known government authority is trusted more than one created by an unknown person. Similarly, certificates issued by highly trusted certificate authorities are considered more reliable. Building this trust requires strong security, proper infrastructure, and strict operational process. Overall, public key infrastructure helps securely manage identities, public keys, and encrypted communication while protecting cloud systems from attacks such as malicious intermediary attacks and insufficient authorization. Now let us discuss Identity and Access Management, commonly called IAM. IAM is used to control who can access cloud resources, what resources they can access, and what actions they are allowed to perform. Think of it like access control inside a company office. Different employees have different permissions. For example, students may access classrooms, faculty members may access staff rooms, and administrators may access confidential records. Similarly, IAM manages user identities and access permissions in cloud systems. It mentions four main components of IAM. One is authentication, authorization, user management, and credential management. Authentication verifies user identity using usernames, passwords, biometrics, or certificates, whereas authorization decides what resources the user can access. In the case of user management, it handles activities such as creating accounts and resetting passwords. Credential management maintains user identities and access rules. So overall, IAM helps prevent unauthorized access to cloud resources. Now let us discuss single sign-on, commonly called SSO. In cloud computing, users often need to access multiple cloud services. If users have to log in separately for every service, it becomes time consuming and inconvenient. Single sign-on solves this problem. With SSO, the user logs in only once and the authentication information is shared across multiple cloud services. Think of it like entering a large amusement park. Once you buy the entry ticket and enter through the main gate, you can access different rides inside without purchasing a new ticket each time for every ride. Similarly, in single sign-on, after successful authentication, the user can access multiple cloud services without repeatedly entering the login credentials. This improves user convenience, faster access, and centralized authentication management. Now, let us understand how single sign-on works using this diagram. First, the cloud service consumer sends login credentials to the security broker. The security broker acts like a central authentication authority. After verifying the user credentials, the security broker generates an authentication token containing the user's identity information. Now, instead of asking the user to log in separately, this token is automatically shared with cloud services A, B, and C. As a result, the user can access multiple cloud services using a single login session. So, the security broker helps maintain one common authenticated session across different services. This diagram explains how single sign-on works across different cloud environments. Here, the security broker receives the user credentials and then propagates the authentication information to different ready-made environments located in separate clouds. Think of it like using one university identity card to access different departments inside the campus. Even though the departments are separate, the same identity card is accepted everywhere. Similarly, in cloud computing, the security broker manages authentication between different cloud platforms. The user does not need to log in separately for each cloud because the broker handles the authentication process in the background. In the next part, we will continue with the remaining topics including Kerberos authentication, one-time password, virtualization security, hypervisor threats, and trusted virtual machine monitors. Thank you.